Eye level with Santiago Peak, settling a gentleman's bet. So here's a disclaimer for you. This video contains no proof. It is not being offered as proof of anything. It's merely an interesting anecdote. Okay? Use this video as inspiration for your own future field explorations. I'm a big advocate of getting outside and then actually making your own measurements out there in the field. So here's the scenario. Water levels in mountains. You may remember John McIntyre. About a year ago, he made a video called Flat Earth, a Mountain of Evidence. So recently, he made a video called Flat Earth Water Level Test Number 2. Actually, when I say recently, I think this might have been 6 months ago. But he's been taking water levels off into the mountains and photographing them against distant peaks. So a water level is simply two containers of water connected by a hose or a tube, and water tries to find its own level. Right? So if you have, you can connect a line, a virtual line between the water levels on both of those containers, that will be level. And one of the things John points out is that it's sort of a virtual body of water. Okay, so if those two guys are 20 feet apart, it's almost like those guys are standing in a pond that is 20 feet wide. Okay, or standing in a pool. So a water level is sort of a nice way of leveling things out there in the field. So John actually made a 60-foot water level. So he's up there in this parking lot in this up in the mountains in California, and he made a 60-foot water level. You could see that in the lower right corner with the green hose and the two reservoirs with red liquid in them. And so he sights down along the containers. They're held up by tripods. And here's a zoomed-in view, but I've erased the mountains because that's the punchline of the video. So we can see that we are looking level. The camera, he's very carefully leveled the camera, and the camera is level with these two containers. And because they're 60 feet apart, we're getting pretty good precision here. All right, so here's another zoomed-in view, and I've erased the mountains. But so it should be obvious that we are looking dead on level with those two containers. So let's introduce our three gentlemen. First off, we have Reggie, who says, "I believe the Earth is flat." And we have Joe, who says, "I know the Earth is a globe." And then we have Mick. Long-distance sightings on the horizon frequently look slightly higher due to refraction. Okay, so here are three characters. So Reggie believes in a flat Earth. And the observer point where John parked his car is at about 5,100 feet, but Santiago Peak is about 5,700 feet. So that means that the mountain should look higher than our eye level. All right, so our eye level should hit the mountain 600 feet below the actual mountain peak. That's what Reggie says. Well, Joe says that the Earth is a globe. So at, I think it's like 41 miles distance, the curvature drop should be 1,200 feet. So let's drop that mountain down 1,200 feet, which means that the eye level, if you do the math, would be approximately 600 feet above the mountain peak. So that's what Joe is predicting. And now let's bring in Mick. So Mick says, yeah, the Earth is a globe, but there is something called standard refraction, or just atmospheric refraction. So he is estimating that because of refraction bends light downward, which means that distant objects appear slightly higher than they actually are. So he says that the mountain should appear slightly higher, which means the eye level should be only 470 feet above the mountain peak. All right, so let's just put in one mountain, and let's figure out where these three gentlemen are estimating eye level to be. So we have Reggie down there. He believes the Earth is flat, so the eye level should be 600 feet below. Joe says the Earth is a globe, so he says 600 feet above. And then Mick estimates 470 feet above because he's using standard refraction. So a few words about standard refraction. So atmospheric refraction is affected by many factors: humidity, pressure, temperature, elevation, weather, distance, and angle of view. And there's no way of calculating with any accuracy an exact value of atmospheric refraction. I mean, it just goes through. Like, for example, in this view, it's 41 miles. So 41 miles of air. There's no way you'd be able to measure all these things in 41 miles. So we have an estimate, okay? And standard refraction is just an estimate. So all things being equal, standard refraction just gives an average value under average conditions. Now, when you talk about average, you know, who's average? Like who's saying what's average? So different people actually calculate standard refraction differently. And of course, all things are never equal. So in this diagram, which was made by a fellow named Easton, he says standard refraction is 4/3, or he's using it as part of the calculation, 4/3 Earth radius. Whereas Metabunk uses 7/6 Earth radius as their standard refraction calculation. So let's go to the actual mountains. Santiago Peak, and the smaller mountain is Modeska Peak. It's named after a Polish actress. So here's the Wikipedia entries giving you the latitude, longitude, and the elevation, some data there. So let's go to Peak Finder, and the observer location is the location where John set up his camera, and we're zooming in on Santiago and Modeska Peak. So let's actually zoom in on this little rectangle. We're going to sort of zoom in, take a little picture there, and let's fade in John's image. Okay, and it's, you know, in making this video, I was actually going back and forth, and like even some of the bumps, you know, line up with bumps in Peak Finder. They really did a nice job. So what we're going to do is we're going to do pixel math, which means we can actually measure pixels on the screen and translate that into feet in the real world. All right. First thing I'd like to tell you is that delta, Greek letter uppercase D, Greek letter delta means change in. Okay, so we have delta x, which would be change in the x value, delta y, change in y, etc. So now this image isn't perfect because the video was handheld, but we can still do some pixel math. So we have Santiago Peak and Modeska Peak. So let's figure out where these things are on the map. In the upper right is the observer, John, that's where his camera was, and then the lower left we have the two mountains. So let's zoom into the lower left. Again, there are the two mountains, and then let's zoom in further. So in red we have Santiago Peak, and then in yellow, the yellow star is Modeska. Now, we can actually measure the distance between these mountains, about 4,500 feet. Now, here's the thing that we want to avoid. Now, we're very fortunate in this situation in that both mountains are the same distance, pretty close to the same distance away from the camera. So what if you had two other mountains where they were represented by those purple diamonds? In red, you'd measure the actual distance between the mountains, but that's not good for pixel math because from our viewer, 41 miles away, the arrow in blue is the apparent distance between the mountains. So it's very important if you do pixel math on your own that you make a distinction between the blue arrow and the red arrow. So don't just plug in the value of how far they are apart. That may mess up your pixel math. But in our case, we're very fortunate because both Santiago Peak and Modeska Peak are almost exactly the same distance from our camera. All right, so let's do the pixel math. First, we'll do the delta x, the x, how many pixels apart, and it's about 649 pixels. Well, in the real world, that's 4,500 feet. So that's about 7 feet per pixel. Now the delta y, represented by green, 30 pixels for 190 feet, that's about 6.3 feet per pixel. Now please notice these two values are not the same, but you know, like you might take an average, you know, 6.5, 6.6 or something like that. But also remember that this was from a handheld, this was a still from a handheld camera. So, you know, take this with a little bit of a grain of salt. All right, let's talk about the gentleman's bet. So again, just to remind you, this is where they were guessing eye level would be versus Santiago Peak. So let's go back to our original imagery. Now I am erasing. So, you know, here was the water level, but I erased the mountains. Now here I'm covering over the water level and I'm zooming in on the mountains. Santiago on the left, Modeska on the right. And so we'll just do the pixel math again. So we've got the delta x, we got the delta y, and because the camera was leveled in this case, the pixel math is really, really close. So we're going to say 14.6 feet per pixel. Now let's take the three gentlemen and let's do pixel math with their estimates. So Reggie says that because the Earth is flat, eye level will be exactly 597 feet lower than the peak. Well, how does that translate into pixels? It's 40 pixels, about 41 pixels. So that's where Reggie says eye level will be. Joe says the Earth is a globe, so he used the Earth curve calculator, but he put in an eye height of 0 because all he was interested in was curvature drop. He was not interested in obstruction. So that gives him a curvature drop of about 1,200 feet. All right, so that translates into 41 pixels. So in purple, there's Joe's estimate of eye height, or eye level, I should say. And now Mick. Mick says the Earth is a globe, but he likes to use standard refraction as an estimate. So he used Metabunk. He actually put in an accurate viewer height, and he's just going down there to the bottom to where it says refracted drop. So the refracted drop is 1028 feet. So if you do the pixel math, then his eye level will be 29.4 pixels higher than Santiago Peak. So there in blue is Mick's estimate for eye level. Okay, so who won the bet? Let's show the full image. So there's the mountains, there's the water level. Who won the bet? Here's the zoomed in view. And the winner got theater tickets. So here's a challenge to you. Why don't you make yourself a water level? You know, it's kind of a fun project, and there's lots of different ways of doing it. I've seen people make water levels of nothing but hose. You know, like there was no 2-liter bottle in the end. It was just hose, 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 and it's a little bit more difficult to manage. But you know, it's a little fun project. Make yourself a water level, or get yourself a dumpy level. Either buy it or rent it, which is a lot more accurate. It's a technical piece of gear, but less fun. So take that piece of gear into the mountains and scope out a pair of mountain peaks and do your own pixel math and see what you can discover. So here's a quote from Alice Carey. There's nothing so kingly as kindness, and there's nothing so royal as truth. Thank you.